So while we were looking at the observations of Planck and Einstein, we were able to kind of be led to two main ideas or two main questions. And that is energy a wave, like light, or particle? And the answer to that is yes. And I know that seems a little odd, but basically we know that matter behaves both as a wave and both as a particle. And we call this feature, this property, the wave-particle duality of matter. And that means that, matter has both wave and particle-like properties. And we see that from the calculations that we've been able to do, and that the interrelationship between Einstein's E equals mc squared equation, as well as the E equals h nu equation that was shared by Planck. So basically, the relationships between these two are reality that has been tested and been observed in different types of experimentation. So de Broglie's main question that he was attempting to answer in his observations and his research was if matter that is clearly particulate, having mass, etc., if that type of matter exhibits wave-like properties. So from other experimentation, we'd seen that items that have wave-like properties also have particulate properties. We were able to show that. And de Broglie wanted to show that the reverse of that is as true as well. So he came up with the equation that you see here. What he's done here is he's manipulated one of the previous equations that we've seen, and instead of having your m equals h over frequency times the speed of light, he substituted in v, and v in this case is not your frequency, this is velocity. Okay, so we're not referring to the frequency here, we're referring to the velocity. So he manipulated this equation that we've referred to before, and he substituted in velocity v. Okay, and basically what this equation allows us to do is to calculate the wavelength of an object at a specific speed. So what's interesting about this is that when we do these calculations, they really only work for small objects. So what do I mean by that? What I mean is that because the mass of an object can be so large or so small, it being in the denominator is going to directly affect the wavelength that is calculated. So h is Planck's constant, m is mass, v is velocity. So if I have a fairly large object, I'm going to have a fairly large overall denominator, which is going to make my wavelength extremely small. And so if we're dealing with larger objects, we may get a wavelength that is not observable. If we're dealing with smaller objects, we can actually obtain a wavelength that is observable. So theoretically, he has been able to show that objects with a specific velocity and specific mass are capable of producing wavelengths, so they do behave as waves as well. But it is most clear because with smaller objects because of this denominator issue that was just discussed. So let's go ahead and let's actually try some calculation to show how this works exactly. So they want us to compare the wavelength for an electron with a specific mass, as you see here, traveling at a specific speed, specific velocity, with that for a ball that has this mass traveling at this speed. Okay, so basically this is two calculations of wavelength, one for an object with relatively small mass and one with an object with a relatively larger mass, comparatively speaking. And we're going to look at the wavelength values that we get for each of these. So we're going to be using this equation. Okay, and we're going to be doing this for two separate sets of data. So we're going to first start with what we're given first, which is to figure out the wavelength of an electron. Okay, so the mass of that electron is equal to the following value. Okay, we also have our speed or our velocity of that electron. Okay, and we do have h, it's a constant. It's Planck's constant, we've seen this before. We're going to check our units as we always do. We have kilograms, we have meters, seconds, seconds. Okay, so we look like we're on the right track. Please remember that 1 joule is equal to kilogram meter squared per second squared. Okay, so we know that we're in the correct ballpark of units. So we can go ahead and plug everything in to the equation on the left-hand side. So our wavelength is going to be equal to 6.6262 times 10 to the negative 34th joules times seconds divided by 9.11 times 10 to the negative 31 kilograms times 1.0 times 10 to the 7th meters per second. Okay, if we plug this into our calculator, we end up with 7.27 times 10 to the negative 11. Okay, and then our units, if we look at this here, if we plug in this value for our joules and multiply that by seconds, we'll end up with kilograms meters squared per second. And if we check these units, seconds and seconds cancel, meters and one of the meters cancel, kilograms and kilograms will end up canceling, so we're left with meters as our units, which makes sense with respect to the wavelength that is seen here. So this is the wavelength associated with our object, our electron. Okay, now if we do the same type of calculation for our ball, we know that our constant is going to be the same because Planck's constant. I'm just going to put this into the units that would be anticipated if we plugged in our conversion here. We're going to put our mass, and then we're going to put our velocity here. And if we go ahead and plug this into the equation, put this into our calculator, we end up with the following value. If we check our units like we have, kilograms cancel, meters is what's left over, and this is what we get with respect to the wavelength of the ball. So if you look at these two values that we've calculated, notice the wavelength of the electron is much larger than the wavelength of the ball here. And so, you know, there's an observable range that we have, but as we get into larger objects, the wavelengths get so small that they're, you know, difficult to observe with the instrumentation and equipment that we have now. However, theoretically, this ball, in fact, does have this specific wavelength. So this ball with this specific mass and this specific velocity has a wavelength and is therefore both a particle and a wave. And the same is true for the electron. It behaves as both a particle and a wave. So de Broglie was able to utilize this equation to show that objects that have mass, that are distinctly particulate, have waves. And he's showing that this is true with an object such as an electron, which in previous examples has been shown to have wave-like properties as well. So this is how they came about the wave-particle duality of matter and solidifying it as the concept that we adhere to.